So this week we'll be looking at the second and final part of sequences, focusing on quadratic sequences. Before we get into the main topic for this week, it's worth pointing out a few more special sequences. I guess should be some quote marks on the word special there. They are triangular numbers and square numbers, and you'll kind of know these from other things, but it's worth pointing out they are sequences and they're related to what we're doing. Triangular sequences have basically the rule that you add one more on each time. So this is going up by 2 and then 3 and then 4 and then 5. And another way of visualizing them is the number of dots it takes to make a triangle if you increase the size of the base of the triangle by 1 each time. So you can see there that we used 1 dot and then 3 dots and then 6 and then 10s because you're adding on a row of dots that's one bigger each time. It's got this nth term, which you are not going to be asked to remember or anything, but it's nice to be complete. And also there's the square numbers. Square numbers are actually going up by 2 each time, but they're also just the square numbers that you're familiar with. And we can also think about them as the number of dots it takes to make each successive square. So it's 1 dot, 4 dots, 9 dots, etc. And their nth term is just, well, n squared because it's the square numbers. So the reason that I bring those up is that those are both quadratic sequences, and we want to talk about what quadratic sequences are and how we can recognize them. So one of the triangular numbers went 1, 3, 6, 10, and the amount they're going up by is changing each time. It goes 1, 2, 3, 4, but the difference between the amounts it's going up is constant. That's what's called the second difference, and you can tell a quadratic sequence because its second difference is always the same. So let's see, we've got a quadratic sequence here, 4, 7, 12, 19, etc. That goes up by 3 and 5 and 7, and those are all different numbers, but its second difference is going up by 2 each time. Its second difference is constant. And if we wanted to get the next number, we would add another 2 onto the difference, so it would now be increasing by 9, so our next term will be 28. We do the same thing here. This goes up by 40 and 50 and 60. So the second difference, which is constant, is 10. So that means the next number would be going up by 70. That would be 250. And that's how you identify a quadratic sequence. Not all sequences have a constant second difference either. One good example is the cube numbers. This is like 1 cubed, 2 cubed, 3 cubed. That goes up by 7 and 19 and 37. And actually let's add on one more because I think we're going to need it. And 61. The second difference goes up by 12 and then 18 and then 24. And you'd actually have to get to the third difference to get to something which is a cubic sequence. Quadratic sequences involve an n squared and cubic sequences involve an n cubed, and we're going to be focusing on quadratic sequences today. So we're going to jump straight into finding the nth term for a quadratic sequence, and I'm doing this a little differently to how I normally would. I think this method is a bit quicker, but it does remove a little bit of the algebraic understanding. We'll give it a go and we can have a look at the other method in time if we need to. So method consists of 3 steps to find basically the value of a, b and c that we're going to put into this general purpose formula. Okay. So first step, find the second difference. So we just talked about that. So that's where we find the difference between the numbers, and then we find the second difference between them. So it goes up by 2. So in this example, our second difference is 2. Halve this to find a. So a is equal to 2 divided by 2. It's equal to 1. There we go. Step 1, done. Step 2, find the 0 term. This is c. Now the 0 term is, as was true in linear sequences as well, what happens if you go back 1? We have to be a little bit careful here. So we'll say, okay, well, the difference has to decrease by 2. So the difference has to be 1. So this number here must be 3. Our 0 term is 3. And that's equal to c. Cool. And then the first term is a plus b plus c. So this was our first term was 4. So we can say 4 equals a plus b plus c. So 4 equals, what's a? A was 1. B we don't know. C was 3. So 4 equals 4 plus b. So b equals 0 in this case. So putting that all together, we've got that a equals 1, that b equals 0, and c equals 3. So according to our formula, it is an squared plus bn plus c. So that is 1n squared plus 0n plus 3. Now we can definitely make this nicer. Instead of saying 1n squared, we would just say n squared. We wouldn't write 0n, we'd just write plus 3. So maybe that would be our final nice looking answer. But that's the steps. Second difference, zero term, and then first term. So let's run that through a few more times because it's, it is a 3-step process. It's one that we've got to remember. So first step, find the second difference. So we are going up by 40, 50, 60, 70. So our second difference is 10. Okay. Halve this to find a. So 10 divided by 2 is 5. So a equals 5. Okay. Then we want to find the 0 term. So remember, we have to be careful here. We have to put in the second difference and the first difference, and we can figure out that our 0 term is actually 0 in this case. So we can say c equals 0. Lastly, the first term is a plus b plus c. So remember, our first term is 30. So I'm going to say 30 equals 5 plus b plus 0. So 30 equals 5 plus b. So b is 25. And then we just need to put all of those in the right place in the formula. So it's an squared plus bn plus c. So it becomes 5n squared plus 25n plus 0. And we've maybe tidied that up to just 5n squared plus 25n. Cool. Let's do one more to make sure we got the pattern here. Find our second difference first. So we are going up. This is a plus 4. This is a plus 8. Be careful about your signs here. So the second difference is 4, I think. So, yep. So our second difference is 4. 4 divided by 2 is 2. So a equals 2. Find the 0 term. So if we go back one to our 0 term, the second difference would still be 4. The first difference would then be plus 0, so that would be minus 7. So our 0 term is c, so it's minus 7. And lastly, the first term is a plus b plus c. So remember, this is our first term. So we're saying minus 7 is equal to a, which is 2, plus b, minus 7. So be careful with your signs here. 2 minus 7 is minus 5. So we're saying minus 7 is equal to b minus 5. And then we need to add that 5 to the other side. So minus 2 is equal to b. And you could also check, does 2 minus 7 give you minus 7, which it does. So there's our answers. So we got 2, minus 7, and minus 2. So putting it all together, we have an squared plus bn plus c. That would be 2n squared minus 2n minus 7. So yeah, really powerful little shortcut method this. Gets you to the answer pretty quick with some very basic maths. At this stage, I would like you to pause, have a go at these two, and then we'll fill them in when you've unpaused. In 3, 2, 1, let's go. Okay, step 1, we want to find the second difference. The second difference is 10. I'm going to fill in some of the other stuff as well as I'm here. So we know that it's going to be a minus 3 there, so that must mean we had 6 there, I guess. Yeah, 6 as our 0 term. Okay, so we've got everything in place here. So our second difference was 10. So we go 10 divided by 2 is 5. So a is equal to 5. Our 0 term is equal to 6 because we've got that by doing the opposite of minus 3 there. I think that's something you have to be careful with your signs there. 7 take away 10 takes you to minus 3. Then you have to think 6 minus 3 takes you to 3. And then our 0 term, which is here, our first term rather, is equal to a plus b plus c. So it's equal to 5 plus 6 plus b. 3 is 11 plus b. So b is, take away 11, minus 8. So our nth term here is 5n squared minus 8n plus 6. Now you might be thinking, how do I check these are right? And obviously one way you can do it is you can substitute in some values and see if they work. So say I was looking at this third term in this sequence, which is 27, and I wanted to check that was right. I could do 5 times 3 squared minus 8 times 3 plus 6 and see, does that give me 27? And well, that would give me 45 minus 24 plus 6, that's 21 plus 6, so yeah, that is equal 27. So remember, you can always check if you're not sure, which I was a little. Okay, second one, going down by 2, then going down by 6, then going down by 10. So our second difference here, unusually, is negative. It's minus 4. If we want to continue this process, we must have come from 2. So what did we add to get to 10? So this was 8 here as well. So we can go through the process again. Minus 4 divided by 2 is minus 2. So a is minus 2. Our 0 term we've just worked out as being 8. So c is 8. And then our first term, which is 10, is equal to a plus b plus c. So it's equal to minus 2 plus 8 plus b. So 10 is equal to 6 plus b. So b is equal to, take away the 6, 4. So our sequence here is minus 2n squared plus 4n plus 8. And again, we could check it if we wanted by subbing in a value and seeing if it gives us the sequence, but I'm going to trust it this time. Okay, so just like with the linear sequences, they can give you fractions, which are a couple of different sequences mashed together. Just remember that the way to approach these is to do the top and the bottom separately. So we'll do the top first. That's 12, can't write, 25, 44, 69, 100. So we'll find the first and second differences. So it's 13, 19, 25, and 31. So the second difference is 6, so that's good. So 6 divided by 2 is 3, so a equals 3. Then we want to go back and find the 0 term. So we'd have to go back another 6, so that would take us to 7, and then go back another 7, that would take us to 5, so there's our 0 term. So c equals 5. And then lastly, the first term, which is 12, is equal to 3 plus 5 plus b, which is 8 plus b, so b equals 4. So our nth term for the top is going to be 3n squared plus 4n plus 5. And then for the bottom, that went 21, 46, 83, 132. Let's just do the 3 of them. That's going up by 25 and 37 and 49, I think. So our second difference is going to be 12, which is good. So we'll go 12 divided by 2 is 6, so a equals 6. Then we want to go back one, so we know the second difference is always 12, so that means our first difference is 13, so that means we started at 8, so c equals 8. And lastly, we want to use the first term, so we're going to say 21 is 6 plus 8 plus b, which is 14 plus b, so b equals 7. So our answer there would be 6n squared plus 7n plus 8. So what do we do? Well, for our overall nth term then, put the top on the top, 3n squared plus 4n plus 5, and our bottom on the bottom, 6n squared plus 7n plus 8. Great question, that. Now the last little thing you could do with these quadratic sequences is you could use them to find out positions within the sequence. So here's an example. How do we find a position of 1, 4, 6 within this sequence? Well, do the same we did with linear, set them equal to each other and solve it. It's just the thing that you'll be solving will be a quadratic equation of some sort. So set it equal to 1, 4, 6, and then we want to make one side 0 if we're solving a quadratic, so we will subtract the 146 to get 0. And then this is a multiply and add situation. We want to find two numbers that times to minus 170 and that add to 7. That might seem quite tricky, but they're actually quite nice, these ones. This is 17 and minus 10. So there's our brackets. N plus 17, n minus 10 is 0. You could also use the quadratic formula, I suppose, but this feels like factorizing time. And remember, we need to change the sign for what n is equal to. So n is minus 17 or n is 10. And we're going to take the positive one of those because obviously we can't have the minus 17th number in the sequence. So it's the 10th number. Cool. Similar question, is 133 in this sequence? Well, we do the same thing. And basically it'll be in the sequence if what we get out of this is a whole number for n, and if it's a decimal it won't be. So it's a sequence, so we subtract the 133, we want to make one side equal to 0, so that's take away 126. And now something nice we can do is we can divide everything by 2. It's solving an equation, it's not going to change anything, and it'll make it way easier to factorize. So we want to find two numbers here that times to minus 63 and that add to minus 2, and those are minus 9 and 7. So we can factorize this to n minus 9 and n plus 7, and then change the sign so n equals 9 or n equals minus 7. We're going to go with the positive number, and that is a whole number as well. So yes, it is in the sequence, and we can say it's the 9th number in the sequence. Another way you could do that is with trial and error. You could sub in different values of n and see what you get to. I wouldn't recommend it, but if you don't like solving quadratics, it's definitely a way around that. And the last thing I wanted to talk about was recurrence relations, which are something that was going to be more expanded on when we do iteration, but you can be asked to generate a sequence that's given to you in this sort of format here, and I just wanted to talk about it. So this is basically a different way of showing a term-to-term rule. What I would do is you've got the un plus 1, that's talking about the next term, and the un, that's talking about the current term. So n up to n plus 1, where you are to the next step. And we've also got this u1, and that's just going to stand for the first term. So we can see here that this first sequence is saying take the current term and add 5 to it, and that'll give you the next term. So the rule is just add 5. So our sequence would be 3, 8, 13, 18, ... Fair enough. First three terms are 3, 8, and 13. Okay, what about this second one? So to get the next term, you do 4 times the current term, and you take away 3. So our rule here is times by 4 and then minus 3. And again, our first term is 5. So 5 times that by 4 minus 3 is 17. Times by 4 is 68 minus 3 is 65. And there's our first three terms. Just keep going. And then lastly, we've got one which is going to be a bit trickier to work out. This is saying to get our next term, we do 5 divided by the current term plus 5. Okay, so we go, I don't know how we'd write this in terms of word, but we do 5 divided by the current plus 3, I guess. That's kind of saying the same thing. Well, let's work it out. And we got our first term is obviously 3. Start with 3. Our second term is going to be 5 over 3 plus 5. So it's going to be 5 over 8. And our third term is going to be 5 over 5/8 plus 5. That's not very pleasant, so I think that's the point that I'd probably type that in my calculator and see what it gives me. Unfortunately, it tells me that that horrible looking thing is literally just 8/9, which is nice. So there's your first three terms. And that's the end of sequences.